Hello everyone, my name is Yaoyu Li. In today's presentation, I will present my midterm report of a systems engineering case study for the class Introduction to Systems Engineering. In today's presentation, I will select the National Polar Orbiting Operational Environmental Satellite System known as NPOESS as the model for the systems engineering case study. First, it will focus on the NASA's past analysis and research of environmental satellite systems, following with the description of the NPOESS program earlier concept phases to validate that there is a real need for the NPOESS system, not only technically but also economically. Later, I will explore potential performances is required for the NPOESS system to accomplish its perceived missions through the concept definition phases. Then I will give a more clear pictures of this system containing its key characteristics that would achieve the most beneficial balance between the capability, the operational life, and the cost. At last, the challenge section, I will illustrate the poor cooperation among the different system agencies and severe management problems that will threat the whole process to the development of the system. Now let's address the first question. What exactly this NPOESS system is? The National Polar Orbiting Operational Environmental Satellite System is a satellite system which can monitor Earth's land, ocean, and the atmosphere to provide data and imagery for weather forecasters, academics, government agencies, and the military. The goal of the NPOESS system is to improve the nation's space-based remote sensing capabilities for environmental monitoring and global change assessment. So now let's move to the next part, which is the history of environmental satellite systems. Why do we want to care about the history of those kind of engineering systems? Just because the system engineering process which are used in today's complex project has matured based on well-founded principles and heuristics from the past development. Therefore, before going into the concept development stage of the NPOESS system, I have to first review the background and past analysis of engineered systems for environmental satellite programs. There are many examples and techniques which provide a basis for past failures and modifications which must be considered for the concept exploration for the NPOESS system. In this session, we mainly focus on the three cases. The first one is Vanguard 2, and later it is the television infrared observation satellite, and the last one could be the tropical rainfall measuring mission known as the TRMM program. So as earlier as 1928, Human Potnik, a Austrian rocket engineer, first mentioned the idea of using orbiting spacecraft for detailed, peaceful, and military observations of the ground. But until 1958, the earlier prototypes of Tyros and Vanguard satellite systems were created. According to a NASA report, on February 17th, 1959, the first weather satellite, Vanguard 2, was launched. It was designed to measure cloud cover and resistance, but this system fails to evaluate requirements and specifications for the effectiveness before beginning the program. Its poor axis of rotation and the elliptical orbit make it be incapable of collecting a significant number of useful data. After conducting several more weather-related experiments, including the Explorer 6 and 7 satellites, the NASA launched the first successful weather satellite named TAROS on April 1st, 1960, which operated for about 78 days and paved the way for the NPOESS programs. And in the earlier life cycle of TAROS program, system engineers develop an effective system concept and architecture. The TAROS concept formulation was rigorous and very traceable to user needs. And the time moved to the late 1970s. Polar orbiting satellites such as the Tropical Rainfall Measuring Mission Program, known as TRMM, began to relay wind information near the ocean's surface, starting with a microwave imagery, which resembled radar displays, significantly improved the diagnosis of tropical cyclone strength and location during the 2000s. The TRMM program was structured to address risk in several ways throughout the multi-phase program, where key risks were known upfront. The contractor and the government use a classic risk management approach to identify and analyze risk, and then develop and track mitigation actions. Identified technical risks were addressed at a weekly chief engineering meeting and often tracked by technical performance measures. The program office would issue a request for proposal to several bidders for developing concept and preliminary designs. Then one contractor would be selected to continue development. This approach not only provides creative solutions through competition, but also help in defining a low risk and more clearly defined development of this program. So by learning these three environmental satellite systems, it can help us in exploring of both successful and unsuccessful methodologies, process principles, and tools to evaluate the outcomes of alternatives at the system levels of the NPOESS program. So let's look at the needs analysis phase. Do we really want a system like an NPOESS system? Do we really need this kind of a system? The answer should be yes. Then why? Since the last century, environmental satellites have been applied widely in the operations of both military and civilian agencies. Those satellites provide information used for weather forecasting, monitoring long-term trends in climate conditions, planning for military operations, and disaster relief. The United States government realized the huge impact brought by the environmental satellite programs. They invest almost $10 to $20 billion every year in those kind of programs. And this positive financial environment allows a number of military and civilian programs are now in operation. But some of those satellites will reach the end of their useful lives in space over the next few years. Based on the design life theory, every satellite program is designed and built to operate for a certain minimum period called the design life. Satellite replacement schedules are typically based on a quantity called the mean mission duration, which combines both the design life of a satellite and the likelihood of that the satellite will file for other regions. For example, if the launch rocket fails or if some satellite component breaks down, once the Department of Defense, the National Oceanic and Atmospheric Administration called NOAA and the NASA found that their satellite system are reaching the end of their operational life and stopping to function at some level. They can launch new satellite systems to replace the old ones to avoid the discontinuities of system replacement. Those three agencies need to storage several more satellite systems awaiting launch. Meanwhile, incubate some new programs for the future. In this case, the NPOESS program need to be designed to replace the current generation polar operational environmental satellites known as POESS program, managed by the Department of Oceanic and Atmospheric Administration NOAA, and also the other satellite system it will be replaced to is the Defense Meteorology Satellite Program known as DMSP, managed by the Department of Defense (DoD), needs to be built. So we got the sufficient reasons for the NPOESS system to be created. So the NPOESS system also can help to reduce the duplication and the production operation cost by those POESS and the DMSP system. After we make sure that we have to make this new converged system to be real, then how can we achieve this goal? This is the main topic we need to discuss in the concept exploration phase. In this phase, the integrated program office of the NPOESS program formed by the DoD, the NOAA, and the NASA suggested three options that the whole research team has been discussed for designing the initial prototypes of this new converged satellite system. Each option is built around a core set of three types of instrument, including a visual infrared imager, which is used to determine the presence and properties of the clouds. The next one is the microwave imager sounder, which is used mainly to determine the atmospheric humidity and the temperature as a function of altitude. The last instrument we care about is a space environment sensor, which is used to determine the conditions in outer space that affect the satellite operations. Those three kind of options that are made by the IOP is different because the different side of the instrument. So the first option would provide the most capable as well as most expensive satellites, and would include upgraded version of all three instruments. The second option would reduce the cost by replacing the more capable microwave imager sounder and the space environment sensor instrument than the version carried on the current generation of POESS and DMSP satellites. And for the third option, would reduce the cost even further by using the visual infrared imager and the microwave imager sounder carried on current generation satellites, as can be seen from the table 1. Option 1 would carry the all upgraded instrument. All the advanced instrument should be in the option 1. And for the second option, it will be carried the current generation version visual infrared instrument and upgraded microwave, and space environmental instruments. Option 3 would carry the current generation visual, infrared, and microwave instrument, and the upgraded space environmental sensor instrument. The IOP also expected the satellite in the first option would be capable of measuring a total number of 37 EDRs, that is, environmental data records, including all 6 EDRs that the endpoint system had defined as key performance parameters, KPPs. Each of 2 satellites that all this system needs would cost about 1.2 billion to manufacture, and the total program acquisition cost, including supporting data handling, systems engineering, and program management cost, would be about 4.2 billion. If the cost for large sports, satellite storage, and on-orbit operations through the year of 2037 are included, the total program cost for the first option would be about 6.1 billion. The satellites in the second option would have less capability, measuring a total of 30 EDRs, including all 6 KPPs. They would cost about 700 million of each satellite to be produced, and the total program acquisition cost would be about 3.2 billion, and the total program cost, including operational through 2037, would be about $4.9 billion. In the last option, the third option, with the lowest cost and capability, would measuring only 25 EDRs, and it's only including 4 of the 6 KPPs, so it will miss 2 KPPs, and the unit production cost would be about $400 million. The total program acquisition cost would be about 2.7 billion, and the total program cost would be about $4.4 billion. So in this phase, the IPO also explored other possible alternative approaches for designing the earlier model of the endpoint system, which may cost a varying amount of cost. One alternative approach is to delay the start of endpoints development to reduce the near-term cost. Another one is to field sensors on several small satellites rather than a single one. All of these options that the IPO exams makes a preparations for the next phase of this designing procedure of this endpoint system, so which is the concept definition phase to the system, and in this phase we will choose a more preferred plan for us to implement. So in this phase, the concept definition phase, the IPO used the quantity of environmental data records known as EDRs, and the key performance parameters, KPPs, and the facts of 3 main instruments of satellite, and the cost of each options to compare the capability of endpoints options and select the preferred one. So let's look at the first standard. Is the environmental data records, EDRs. So what the EDR is? When the satellite data first arrived, satellite data are considered as raw data. To make them useful, and the processing centers format the data so that they are time sequenced and include Earth's location and calibration information. After formatting, these data are called raw data records. The centers further process these raw data records into channel-specific data sets called sensor data records and temperature data records. These data records are then used to derive wider product called environmental data records. According to the information that concept exploration phase have been provided, the first option would measure the 37 EDRs. And the option 2 will measure about 30 EDRs, and the third option would measure only 25 EDRs. So the endpoints satellite was expected to measuring 32 EDRs. After the comparison, the research team found that the option 1 has an increase in capability about 5% for receiving the EDRs, and the option 2 has no great changes in the capability of receiving EDRs, but for the last option, the third option, has a decrease in capability of about 15%. Let's move to the next part, is the key performance parameters comparison. So what is KPPs? The KPP performance parameters means what is the critical, what is the significant performance goals are in the United States Department of Defense acquisition and the joint capabilities, integration, and development system process. The KPPs represent the desired operational goals. They have a threshold representing the minimum acceptable value achievable at low to moderate risk. In this table, we can see that the option 1 and 2 satellite would measure all 6 KPPs, but those one of for the option 3 would only measured 2. Only measured about 4 KPPs. The 2 KPPs that the third option would like to miss are the speed and the direction of sea surface, and about another KPPs is the soil moisture KPPs. Those kind of KPPs will play an important role in the planning ground operations. And for the third standard, the IPO care about is the capability of 3 instruments themselves. So in this table, we can see that the visual and infrared imagery used by the option 1 satellites is the newest, is the latest version, and the AVHRR carried on option 2 and 3 satellites is an older instrument that fails on POESS satellites. Both of them can provide continuous imagery as they pass overhead and cover similar areas, but the VIIRS has a higher spatial resolution, meaning it can measure areas as small as 0.5 kilometers to 1 kilometers on one side, while a VHRR can only measure the area 1 kilometers to 6 kilometers on one side, and the VIIRS pixel size varies less over the field of view, making the imagery easier to interpret visually. For the talking about the microwave instrument sounder part, the option 1 and 2 satellites will carry about MIS models. That has the larger antenna would make the spatial resolution of imagery about 3 times better than the AMSUA instrument, which is used in the third option that currently flew on the POES, has an imagery resolution depend on the frequency band. And talking about the environmental sensor part, the IPO mentioned that all of these 3 options, they use the same kind of environmental sensors. So that means the performance of this part are totally the same. After comparing the technical aspect of these 3 options, the IPO compared the cost of them too before they defined an overall optional concept of NPOESS system. For option 1, with all upgraded instrument, the total acquisition cost would be about 4.2 billion, with a satellite production unit of the satellites about 1.2 billion each. And like we talking about that before, option 2, in which the lower cost of a VHRR instrument would replace the VIIR instrument, the total acquisition cost would be 24% less than that of the first one, about only 3.2 billion. And the product unit cost of the satellite would be about 700 million each. For the third option, in which the lower cost VHRR and the AMSUA instrument would replace the VIRS and MIS advanced instrument, the total acquisition cost would be 36% less than the option 1, about 2.7 billion. The unit cost of production for each satellite in option 3 would be about 400 million, or just about 1/3 the cost of the satellites in option 1. So with the considerations of all about the technical and the financial aspect that we have discussed in 2000, the IOP initiate a program definitions to define the NPOESS total system architecture, including space, segment, ground processing segment, and the C3 segment, that is command, control, and communication segment, as well as the sensor space integration part. And the option 1 concept is applied to the space segment designing process. The VIIRS combines the radiometric accuracy of advanced very high resolution radiometer currently flew on POES with high spatial resolutions of operational line scan system flew on DMSP. It has 22 channels grouped into the day and night band, visible and near infrared, short and mid wave infrared, and long wave infrared, with additional special capabilities that can be used to determine ocean colors. And the MIS replaced the microwave imaging capabilities of Japan's advanced microwave scanning radiometer on NASA's Earth observation systems satellites, and the atmospheric sounding capabilities of the special sensor microwave imager sounder on the remaining series of DMSP satellites. So do we expect the whole designing process to be smooth, to be successful? Of course, but there are still some challenges constraint the whole system. So one of the key challenge for the endpoints program is cooperation between the separate agencies of different size with a divergent objective and different acquisition procedures. In order to manage the endpoints program, the Department of Defense, the National Oceanic and Atmospheric Administration, and the NASA formed a three-agency integrated program office. At each agency had the lead on certain engineering activities. The NOAA shoulders the overall program management responsibilities for the converged system and also for the satellite operations. The DoD provides the majority of the acquisition personnel and acquisition structures. And the NASA facilitated the development and the incorporations of the new technologies into converged system. The build of an effective environmental satellite system based on the cooperation of these three departments. However, a report from the Government Accountability Office, known as GAO, revealed that in the endpoints program, NASA experienced challenges with partners not meeting commits within planned funding levels and established schedules. The lack of cooperation among these three agencies make NASA project managers were confronted with unexpected delays that caused NASA to expend about $304 million that could those kind of money could have been allocated for other projects had the instrument being delivered on time. Insufficient cooperation also comprised the final system integration and testing activities and could delay the launch time of the endpoints system, further increasing the launch service and support cost. The NASA is responsible for funding. And talking about the next challenge could be the management problem. As a complex engineering system, the endpoints system contains multiple levels of management, including subcontractor, contractor, program office, and executive leadership, every one of whom serves a distinguished role in managing the program. The Government Accountability Office, that GAO, also documents a poor management phenomena existing in the whole system. The subcontractors' inadequate project management triggered the VIRS sensor development issues. After a series of technical problems happened, the review teams sent by the main contractor and the program office found the subcontractor had divided from a number of contract management and policy directives set out by the Make office and that both management and process engineering were not right. Neither the contractor nor the program office had recognized the underlying problems in time to fix it. After these issues were identified, although the subcontractor's management team was replaced, the part procedures of the NPOESS program was rescheduled and then delayed the whole process of NPOESS launch time by 5 years. So this is the end of my presentation, and in this midterm report case study, the whole process, I have learned that the developing a effective system concept and architecture is one of the most important responsibilities of the system engineers in the earlier life cycle of the program. And the system concept and preliminary design must follow the need analysis rather than process it. In this case, the endpoints program is expected to be a state-of-art environmental monitoring satellite system that will replace the two existing environmental satellite system to provide data and imagery for weather forecaster and the military, academic government agencies to map and monitoring the changes in weather's climate and the other environmental conditions. The IPO explored a range of options, helped the whole system moves forward with its environmental missions. Through comparing the instrument set plans and their cost estimated by their options, the IPO finally can define a operational concept for the endpoints program. So for the later about more information about the whole life cycles of the endpoints program, I will do it in the final project report part. Thank you for listening.